I am Anil Kumar. Welcome to my series on trigonometry. In this video, we'll learn about the graph of cosecant function. We'll also figure out its characteristics. In case you want to learn from me, you can always send an email on the address given. Please check our website for the latest videos on this topic. So basically, we are going to consider the transformed cosecant function a cosecant k x minus p plus q. We'll see how do we graph it, and also we'll find the equation from the given graph. As you know, cosecant is reciprocal of sine function. So the strategy to sketch the graph of cosecant function is to sketch the graph of sine function first, then draw the reciprocal function. As you can see here, we have drawn the sine function here, and once you do that, after that, the reciprocal of the same will give you the cosecant graph, which kind of looks like this, as shown in blue. Perfect. We'll also consider videos. We'll also consider examples where we are going to find the equation from the given graph. As you can see here, if the equation, if the graph of cosecant function is given to you, as shown here, how do we find the equation of this particular graph? The strategy is to find the equation of the sine function first, right? And once you do that, then it becomes easy to find the equation of cosecant function. In previous videos, we learned how do we find the equation of sine function. The formulas which will be used will be to find the axis, it is the average value. Check the maximum and minimum, divide by 2. So that gives you the average value, Q. To find the amplitude, it is the difference of maximum and minimum divided by 2 for the sine function, right? The frequency, or K, will be 360 degrees by the period, or 2 pi by period P if you're doing it in radians. So that is how you could actually get the equation for the primary trigonometric ratio sine function. And then from there, you will get the equation for the cosecant function, correct? With the help of examples, we'll understand all these concepts. Let's begin with understanding how do we relate the function and its reciprocal. Key points to understand is look for invariant points. Invariant points are the ones where the y value is plus or minus 1. Correct? So if you have, let us say, the value of function as y equals to 1, in that case, reciprocal will be 1 over 1, which is also equal to 1. If y is equals to minus 1, then the reciprocal of minus 1 is also minus 1. So these points are called invariant points. They remain same, or you can say common points, on both the function and its reciprocal. That's the whole idea, right? So we know these are the invariant points. If you consider sine and cosecant, well, plus and minus 1 values of sine and cosecant functions, these are the common points, right? The second important thing here is to look into zeros of the functions. The reciprocal of 0 will be translated to a vertical asymptote. So as you can see here, the zeros of the sine wave, these are the zeros for the sine wave. Let me make them with an open circle. So these zeros will be seen as the vertical asymptotes on the cosecant function. Do you see how they are related? Correct. So identify the invariant points where the y value is 1 or minus 1, and also the zeros. Zeros will become the vertical asymptotes as I am showing here now, and Plus and minus 1 values will remain same in both the functions. Perfect. Now that clearly indicates that the domain of the reciprocal function will not include the zeros, right? Because 1 over 0 is not defined, right? Since 1 over 0 is not defined. Now another important thing is to look into the concavity. So as you can see, the sine function, for example, shown here, concave down, and in this portion, concave up. If you look into the cosecant function, the concavity reverses, correct? So the portion where the sine was concave down, cosecant becomes concave up. So that's a very important thing to understand, the concavity. As far as the period is concerned, it remains exactly same. So period will not change. Symmetry. The sine function has odd symmetry. Its reciprocal, cosecant, will also have odd symmetry. So the symmetry is also maintained. In this video, we'll focus on the cosecant function, which as you know is 1 over sine x, where the sine x cannot be equal to 0. Now let's look into the characteristics of cosecant function. As discussed earlier, we know y equals to cosecant x is same as 1 over sine x, where the denominator sine x cannot be equal to 0. So that gives us a couple of important things. These are reciprocal functions, right? So the invariant points are actually the local maximum and local minimum. In the case of sine function, so they remain local maximum minimum in the case of the inverse function also. These are also the invariant points where the y value is plus minus 1. The vertical asymptotes will occur at the zeros of sine function, which is 180n. So if you're working in radians, then it will be n pi, correct? The period for sine function is 360 degrees or 2 pi. So the period for the cosecant function will also remain as 2 pi. Both will have odd symmetry. The domain for the cosecant function, since we are considering the characteristics of cosecant function, the domain will not include the zeros of sine, which are the vertical asymptotes in the domain. So all real numbers except for x, which is not equal to 180n, or which is not equal to n pi, right? So you can always replace 360 degrees with 2 pi, 180 degrees with pi, or 90 degrees by pi by 2 in case you want to work out in radians, right? So the domain of the cosecant function is all real numbers except for the values where x is 180 n, where n is integer. The range, as you can see, is either greater than equal to 1 or less than equal to minus 1. It belongs to real numbers. The graph is concave up for all the positive values and concave down for all the negative values. So this is the graph of cosecant function. You can see concave up, and then negative values, it is concave down. Correct. Now, here is a general formula for the local maximum and local minimum. The local minimum values are these values. Let me highlight the local minimum values for the cosecant. Those were the maximum for sine function, right? So the local minimum values are at x equals to 4n plus 1, 90 degrees times 90 degrees, where n is integers. Now for the local maximum, which are the points mentioned here, these are the local maximum for cosecant functions, 4n minus 1 times 90 degrees, that becomes a general formula. Perfect. So these are the characteristics of cosecant function. Let's take up examples now to understand how do we sketch the transformed cosecant function. So we'll begin with the functions involving vertical stretch and translation. So in this example, we'll sketch y equals to 2 cosecant x plus 1. Well, so there are methods of doing it. We'll actually follow two different methods to illustrate, and then we'll actually adopt the second method. First method here is, as you know, cosecant is reciprocal of sine. So in the expression, which is 2 cosecant plus 1, we could write as 2 over sine x plus 1. And of course, sine x cannot be equal to 0. So the steps involved in this particular case are that first you sketch the graph of y equals to 2 sine x. So that is step number 1. As you can see, we have sketched the graph of y equals to 2 sine x, correct? So once you sketch the graph of y equals to 2 sine x, then you can have a reciprocal of this to get you the graph of 2 cosecant x. So reciprocal means mark the invariant points which are at plus and minus 1, right? And then flip over the concavity. Do you see the concavity? So two things which we have done here is first mark invariant points. Okay, that's number one which we have to consider. And two, what you have to do is flip concavity. Third is zeros to vertical asymptotes, right? So we can actually draw these vertical asymptotes at all the zeros of the sine function. So what you get here is the graph of 2 cosecant s. Let me write this as step 1 and this is step 2. So we got the graph of 2 cosecant x. Now in step 3 you can do the translations. So first sketch the graph of y equals to 2 sine x followed by the reciprocal and then the translation. So these are the three steps which are shown here in the three stages, correct? So ultimately you get the graph of the cosecant function representing 2 cosecant x plus 1. Clear? Perfect. So let me mark these vertical asymptotes clearly here. Okay, it's a very important point. So that was fairly straightforward. So in case of vertical stretches and translations, you need to first sketch the sine function. Once you do the sine function, then mark the invariant points, the vertical asymptotes, and flip the concavity, where the invariant points will be common. So the maximum, the local maximum for the sine function becomes the local minimum for the cosecant function, and the local minimum of sine becomes the local maximum. Perfect. Once you've done this, you can identify the characteristics of the cosecant function. Domain is going to be all real numbers except for the values which correspond to 180n. Vertical asymptotes at these points where sine had the zeros, right? 180n. Period is exactly the same as that of the sine function, which is 360 degrees. And as far as the range is concerned, for the cosecant function in this particular case, since it has been translated 1 unit up in that case, and it is also vertically stretched by a factor of 2, the range is, as you can see from here, that y values are greater than or equal to 2 or they're less than or equal to minus 1. The local minimum is at 2 and the maximum is at minus 1. Correct? So that is how we are going to sketch these functions. Now, let's go to example 2. But before that, let me also discuss the method 2. Method 2 here is to sketch completely the function y equals to 2 sine x plus 1. Now, this is kind of very important to understand. What we could have done here is that we could have actually sketched the sine x function, 2 sine x plus 1 function directly, and then perform the, the inverse, right? So that is another key to the idea of sketching the graph, okay? So that could have been done. So in this case, I will say you could have sketched the sine function. Let me just sketch it now and show you how it makes sense. So these are the zeros, right? So those will be the maximum, 0, correct? So that is the, I'm going to sketch the sine function, as you can see. So like this, if I sketch the sine function as such, which is y equals to 2 sine x plus 1, after that, all those points on the axis where the sine function intersects will now become the vertical asymptotes, and the turning points will be common with the cosecant function, and the concavity flipped will give you the cosecant function, right? So you could do that also. Now this is our method which we are going to use in all our examples to sketch the cosecant function. Okay, so let us see in example 2, how do we sketch the cosecant functions easily, correct? So we'll take up a case where the function is of the type y equals to a cosecant x plus q. So there will be a vertical stretch and a vertical translation, as we saw in the first example. So we'll begin with a very simple case, the parent function y equals to cosecant x, and then we'll see what happens when we translate it 2 units up, and separately what happens to cosecant x when you multiply by 3. That means the amplitude is 3. So in the first case, what I've done here is I've just sketched the sine function, right? So that is the sine function. All the points on the axis are converted to vertical asymptotes, as you can see, and all the points, which are the turning points on the sine function, right? There the concavity has been flipped using the invariant points. So the idea here is step 1, sketch sine function, right? I'm saying sketch sine equivalent, okay? And then this will be a first step. Second step will be uh, vertical asymptotes at intersection of axis and curve, the sine curve, right? So at all these points where the axis will be touching the sine curve, at those points we'll draw the vertical asymptotes, correct? Right. And then third step will be we'll check for the turning points. So these are the turning points, correct? So mark the turning points, and at the turning points, these are invariant points. These are invariant points. They remain same. So fourth step will be concavity reverse. So once you do that, then you get your cosine function, and as you can see, that becomes pretty simple, right? So we have taken the 3 examples. In the first case, we have sketched the sine function. In the second case, we have sketched sine x plus 2, right? Sine x plus 2. And in the third case, we have sketched 3 sine x. So here we have sketched sine x. In this case, we have sketched sine x plus 2 and then the cosecant x. And in this case, we have sketched 3 sine x and then the cosecant, right? So as you can see, it is very simple. Sketch the sine 3 sine x equivalent sine function for the cosecant function. Then once you do that, you know this is your axis. The point of intersections, draw the vertical asymptotes at these points. Correct? So at these points, draw the vertical asymptotes. Where the axis intersects the sine function. And then you can also mark the turning points. These are invariant. They're common to both the graphs. And at the turning points, flip the concavity to get your function. Is that clear to you? So that is our method 2, which we are going to now adopt for sketching cosecant functions easily. Now you can write down the characteristics. I have mentioned local maximum and minimum points for these functions, and also you will notice when you do vertical translations and vertical stretches, the domain, asymptotes, and the period, they remain same for each and every function. They will not change. Correct? As far as the range is concerned, in general, I can write range will be all real numbers and the value will be always greater than equal to q plus a in general, right? And will be less than q minus a in general. The amplitude is a, the axis is at q. And local minimum value is q plus a, and the maximum value is q minus a. So with that, you can write generally the characteristics of any cosecant function. Clear? Now let's take example 3, in which we'll consider the horizontal stretch and the vertical stretch. Sketch the graph of 2 cosecant 1 over 4x and write its characteristics. So as far as this graph is concerned, we'll actually sketch the graph of 2 sine 4x, correct? So 2 sine 4x, 1 over 4x, 2 sine 1 over 4x. So here is the graph of 2 sine 1 over 4x. So this is the amplitude of 2, correct? And the period will be 1440. So we have shown half the wave here. 720 is right there, right? So we have shown half the wave here, period of 720, right? So that is your time period. Now clearly, when you draw that sine function, then at the axis, this is the point where we'll get the vertical asymptote for the cosecant function. Perfect. So those will be the vertical asymptotes. This will be at 720. Okay. And wherever are the turning points of the sine function, at those turning points, the concavity will be flipped, and then you can get your cosecant function. So that is how you can very easily sketch the cosecant function from sine function. Perfect. Now you can mention the characteristics as written here. We know that there will be vertical asymptotes at 720n. So in the domain, these points will not be included, and those are the vertical asymptotes. The range in this particular case will be y is greater than equal to 2 and less than equals to minus 2, right? Local minimum is 2. That is the local minimum point on the cosecant function, and minus 2 is the local maximum as shown here. Correct? Now let's see example 4. In this particular case, we're going to find the equation from the graph, right? So now the question is find equation from graph. So in this example, we are given the graph of the cosecant function, which is right there, and we need to find the equation in the form of y equals to a cosecant kx plus q. So there is a horizontal stretch or compression, there's a vertical stretch or compression, and the axis has changed. So the idea here is that we need to figure out what is the local maximum and what is the local minimum, and from there we can find the amplitude of the sine wave in between. So we'll first work on the sine function. You get the idea, right? So the equation, first find equivalent sine function. Okay, so we'll find the amplitude using the formula which we have already discussed, maximum minus minimum divided by 2. we get an amplitude of 2 in this case. The average values, add them up and divide by 2. Minus 1 is the average value. To find the value of k, check the time period. So k is 360 degrees. As you know, k is 360 degrees divided by the time period p. In case you're working in radians, it will be 2 pi by p, correct? So in case of radians, it will be 2 pi by p. So we get a k value of 3. That gives you the sine function as 2 sine 3x minus 1, correct? So the cosecant will be replace sine with cosecant and remains exactly same. So this is the equivalent value for the cosecant function, right? That is how we get our equation from the graph for the cosecant function. So as you can see here very clearly, that is the sine function which we are talking about. So these are the invariant points, right? And the period here is 120, correct? So the period here is 120. The amplitude is this value, which is of 2, and this value here going down by 1 unit is the q value. Perfect. So that gives you the sine function, and replace sine with cosecant to find the cosecant function. Perfect. So that is how easily we can find the equation from the graph. Let's take more examples. Example 5. Here's another one for you. You can actually pause the video, answer this question, and then look into my suggestions. You need to determine the graph of the cosecant function in this particular case. So the idea is, again, read these values, right? So on the sine function, this will be your maximum, correct? So as you can see here, so that will be your max. Sine will be, this is maximum, this is minimum for sine. Do you get the idea? So from this we get the value of a. 4 minus 1 divided by 2, that gives you 2.5 as the amplitude. Q value will be, add them and divide by 2, which is 1.5. The period was 720 in this case, right? So from here to there it is 720. So 360 divided by 720 gives you the value of k, which is half, and therefore the sine function is 2.5 sine half x plus 1.5. To get the cosecant function, replace sine with cosecant to get your answer. Perfect. So that is how very easily you can actually find the equation of cosecant function from the sine function itself. Here is another example very similar to practice. Example 6. Find the equation from the graph. This time we are working in radians. Determine the equation from the graph in the form of y equals to a cosecant kx plus q. So the strategy, as you know, is to sketch the sine function and then write cosecant function as shown. In this case, this is the sine function which we have sketched. Perfect. So once you sketch the sine function, then read the maximum minimum values and write down. So, well, you could have read maximum minimum from here to get the values in the first case. So you have minus 1 minus 3. These are all negative values. And then divide by 2, you get 1. For the average value, q is minus 1 plus minus 3 divided by 2 gives you minus 2. Value of k is 2 pi by pi. Pi is the period of this cosecant function shown here. And so you get the function as y equals to sine 2x minus 2. Equivalent cosecant function is written there as the answer. Perfect. It becomes very simple because you're good at finding equation for sine function. That is an assumption. Right. Now here is the last example which I'll leave for you as a test question. Now, once again, the steps are kind of like this. Identify these points, right? So write down their values. These are your local maximum and minimum values, right? So you say, what is your maximum value? What is your minimum value, correct? Once you get that, then the value of A will be maximum minus minimum divided by 2. The value of Q is going to be maximum plus minimum divided by 2, and the value of K will be 2 pi by time period. Once you get that, then you write the function y equals to a sine k x minus p plus q. and then you write your equivalent function, which is going to be the answer, which is y equals to a cosecant k x minus p plus q. Is that clear to you? So follow these steps to find the equation of the cosecant function from the given graph. I hope that makes sense. Feel free to write your comments, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.